Hi, so this is going to be your how-to video for how to do molarity and molality calculations. So as you will have heard already in class, but I'll go over it once again, molarity is the number of moles of your solid thing in your liters of solution. So the numerator in our molarity fraction has to be in moles and the denominator is going to have to be in liters. If any of that information is given to you in not moles or not liters, you're going to have to convert. And then finally, our unit for molarity is a big capital N. So as I went over in class, if you're given information in moles and liters, it's very, very simple. So like for this one, you would do your 2.5 moles of MgO over 35 liters of solution, and you would divide that, and then you would get your molarity, which ends up being 0.071, I believe, molar. Okay, so that's going to be your answer for that one. Number two is much the same. And then for, I should say number two, letter B is much the same. Letter C requires an extra conversion step because letter C gives you the amount of solute, the solid thing, in grams instead of moles. So before you do that simple division, you have to convert your grams to moles. So we start with a T-chart, just like we've always done with conversions. We have 16.4 grams of CaCl2 over 1. Then to convert from grams to moles, we divide by our molar mass. So for every 1 mole of CaCl2, that's going to be 110.986 grams. And then again, if you're unsure of where I got this number, I got that from the periodic table, from adding the mass of calcium plus 2 masses of chlorine together. And then that's going to give you 0.148 moles of CaCl2. And then we're going to divide that by how many liters of solution are present, which in this case is 0.614 liters. And once we do that simple division, we get 0.241 molar as our answer. Yes, we are rounding this to 3 sig figs, so that's why it's 0.241. And then letter D is going to be much the same, except for that one in particular, you have to do your grams to moles calculation. And you also have to convert milliliters to liters before you can figure out the molarity. And you're going to do that by very simply moving your decimal place here 3 spaces to the left. So 289.2 milliliters becomes 0.2892 liters. Okay? So that's the first part. For the second part, this asks you to go backwards because in this case, it's saying what mass of solute. So again, solute means solid. So what solid mass is needed to prepare each of the following solutions. So now you're given an amount of liquid and a molarity of the solution. So to do this one properly, you can do it in a couple of different ways. I personally like to set up a proportion because what this capital M means, in case you forgot, is amount of moles in 1 liter. So what this number is telling you, quite literally, is that there is 0.125 moles of K2SO4 in every 1 liter of that solution. Okay? So picture this. I'm going to draw this over here. Picture this for a second. Picture a beaker, and it has some liquid in it. All right? And that liquid has a certain amount of particles. Okay, so that's what molarity is telling you. How many moles, particles, per set amount of volume. Okay, So that's what this is saying. There's 0.125 moles in every 1 liter. And so once you have that, you can then figure out how many grams that is by doing a little T-chart over, and you're going to multiply by your molar mass, because in this case, we're moving from moles to grams. All right, so our molar mass, again, found on the periodic table for K2SO4, is 174.252 grams for every 1 mole. We multiply that straight across, and we are going to get out of that 21.8 grams as our answer. So that one was pretty straightforward. But what happens when we don't have 1 liter of solution, like in letter B? Letter B has only 375 milliliters, and it gives you a set molarity. Once again, the molarity means that there is 0.015 moles in every 1 liter, but we don't have 1 liter. We have a fraction of a liter. So once again, to convert this to liters, you just move that decimal place over 3 points. So we actually have 0.375 liters. So if we refer back to our diagram, what I'm basically saying to you is that if 1 liter contains a bunch of dots, we have a fraction of that. So that fraction is going to contain less of your solid than the whole liter would. So if we set up a basic proportion here, we can solve for how many moles is in that small fraction of a liter. And we do that by cross multiplying. I don't know if you guys have used proportions in math, hopefully you have, but proportions work like this. You multiply that way and you multiply that way. So once everything is said and done, you have 1x, that's the product going this way. And then the product going that way is going to be 0.375 times 0.015. And then we just solve for x by multiplying those two things together. And when I do that, I get x equals 0.005625. So the reason we did that is we wanted to know what x was. We wanted to know how many moles of that solid were in that fraction of a liter that we had. So now we know what our numerator is. Now we know how many moles. And then once we have that number, we can divide by how many liters are present to get molarity, or alternatively, we can take this amount of moles and convert it to grams to get our mass that we're looking for. So remember that this set of problems is asking for mass. So we're going to take that 0.005625 moles, and we're going to convert it to grams by multiplying by the molar mass of what we have, which in this case is sodium fluoride. And if we look at the periodic table, sodium plus fluorine equals 41.998 grams for every 1 mole. We multiply that out and we get 0.236 grams as our answer. So that probably confused you a little bit. Let me do it again with problem C. So once again, we're given a molarity and we're given an amount of liters. So for every 1 liter of solution, there should be 0.35 moles. So we want to know how many moles are in 0.5 liters, because again, we take that decimal place, we move it over 3 times, and that number is x. We cross multiply, just like we did before, this way and this way. We get 1x equals the product of 0.5 times 0.35. Okay, and then we get x equals, once we solve that out, 0.175. We take that 0.175 moles, and now we use a T-chart, and we're going to convert that to grams of C6H12O6. Once we figure out that molar mass on the periodic table, it comes out to 180.1548 grams for every 1 mole. Solve out our T-chart, and we get 31.5 grams as our answer. So, if you have questions on how I was doing that, I need you to talk to me in ELT or in office hours. Consult me for guidance, because again, some of these calculations are very simple. Some of them require a little bit of thought. So if you don't really understand what a solution is, it's going to be very hard for you to think your way through these problems. All right, so let's move on to molality. Molality is going to be a little bit different than molarity. Molality is going to be moles of solute again. So again, moles of your solid thing. But this time we're not dividing by liters of solution. This time we're dividing by kilograms of solvent. So kilograms of your liquid thing. And our unit for molality is this little cursive m, lowercase this time. So for number 3, letter A, that should be pretty simple because again, everything's given to you in the correct unit. You don't need to do any conversions beforehand. So this one is quite literally 3.6 moles divided by 25 kilograms of your water. And once you solve that out, that's going to be 0.14 molal. Okay. Letter B, on the other hand, you're going to have to do a little bit of converting. So that 13 grams of benzene, you're going to have to convert that to moles by dividing by your molar mass of C6H6. And then your 17 grams of CCl4, you're going to have to convert that to kilograms. But once again, that's easy to do. You take your 17.0 and you move this decimal place over 3 times, and you get that you have 0.017 kilograms. Okay. Then after you've done both of those conversions, you can do your however many moles over your 0.017 kilograms, and you'll get an answer. Okay. So those ones should be pretty simple as long as you remember which calculations you should be doing, which conversions you should be doing. Down here, we start getting slightly harder problems, okay? Letter D is easy still, even though it's starting to give you information that you don't need yet. So this is saying, hey, we have 2.89 grams of sodium chloride, and it's dissolved in this many liters of water. It also tells you what the density of water is, which is how you are going to convert that liter amount into a gram amount. Because remember, you need kilograms of water. You don't need liters. So that is done fairly simply, okay? So if you have 0.159 liters, that's the same thing as 159 milliliters, right? And if water is 1 gram for every milliliter, that's also the same thing as 159 grams of water. And if it's 159 grams of water, you can convert that to kilograms by moving our decimal place backwards. So quite literally, we have 0.159 kilograms of water there. Okay? And then this here, you can convert this 2.89 grams of sodium chloride to moles using your normal T-chart function. So that one looks harder than it actually is. However, number 4 has some difficulty to it. So for this, we're given some information. We're given a molarity of sugar, and we are also given a solution density. Okay, so what the molarity means, once again, is that there are 0.840 moles of sugar in every 1 liter of solution. And remember, solution means both parts. Solution doesn't just mean the liquid part. Solution is both. Now, we want to have kilograms of solvent because molality, once again, is moles of solute over kilograms of solvent. So if you weren't sure, this is solid, that's the liquid. But what this is telling us, we know how many moles of solute. We know how many moles of solid because this tells us right here in the numerator. But this is liters of solution in total. And that's different than the amount of the liquid part. So we have to do a little bit of converting. But I'm going to write a note to myself that says, this is how many moles of solute I have. That's what this number is. Okay? But let's take this 1 liter of solution and let's do a little bit of converting to figure out how many grams of solvent are present. We know a couple of things. We know that 1 liter is equivalent to 1,000 milliliters because of just basic metric conversions. And we know that the density of the entire solution is 1.12 grams for every 1 milliliter. So if we take our 1,000 milliliters of solution present and we convert that using our density, using 1.12 grams for every 1 milliliter, we get that in total, the solution is 1,120 grams. But again, that's not the same thing as solvent. That is different. That's total. We need how many grams of solvent are present. So to get that information, we also have to take this number, how many moles of solute are present, and we have to subtract it from the total grams of solution. Okay, so we need to do a T-chart. We need to take our 0.840 moles of sugar, and we need to convert that to grams. And so we do that the way we've always done it. For every 1 mole, that C12H22O11 is going to weigh 342.29 grams. Again, I got that information from the periodic table. We multiply it out, and we get that the moles of solid are 287.53 grams. So if we recall the information that solution equals solute plus solvent, we can take this number and subtract 287.53 grams of solute, and we get 832.47 grams of solvent. So that's how many grams of solvent are present. Now, to get molality, if we recall from up here, molality is moles of solute, which we already know, divided by kilograms of solvent, which we figured out. So we take our 0.840 moles and divide it by this number in kilograms, so 0.83247, and that answer will be our molality. That is going to be 1.12 0.01 molal. Okay, again, that's a lot, but I'm going to do another one so that you can get the idea. So let's move down a little bit. Let's move down to letter B. Once again, I'm going to start over here. We have a solution that is 4.91 molar. That means that there are 4.91 moles of NaOH in every 1 liter of solution. Okay? We know that 1 liter equals 1,000 milliliters. So we can figure out how many grams our solution is using this density right here. So we do one T-chart, starting at how many liters are present, how many milliliters, and we can convert that to grams. So when we do that conversion, we get that there are 1,040 grams of solution present. Next, we have to figure out grams of solvent, and to do that, we have to subtract out how many grams of solute exist in that solution. So we do another T-chart. This time we start with our 4.91 moles of NaOH over 1. We get our molar mass from the periodic table, which if we consult that, it's going to be 39.9969. We multiply our T-chart out, and we get 196.38 grams of NaOH, which is again our solute. We subtract that from our total grams of solution. And that gives us how many grams of solvent are present, which in this case is 843.62 grams of solvent. Now, we go back, we again use this amount because molality is moles of solute over kilograms of solvent. We get 4.91 moles solute over this number in kilograms, 0.844 kilograms of solvent. We do that division, and then right at the end, we get 5.82 molal as our answer. I'm going to leave letter C up to you guys. You are capable of using those two problems that I just did, and you are more than capable of following that pattern for letter C because it is the exact same pattern. Okay? Now let's talk about number 5. Number 5 is a challenge. Number 5 asks for both the molarity and the molality of ammonia if it is in a solution composed of 30.6 grams of ammonia in 81.3 grams of water. Our density of the solution is 0.982 grams per milliliter, and the density of water is 1.00 grams per milliliter. So let's recopy our definitions of molarity and molality. Molarity equals moles of solute over liters of solution. Molality equals moles of solute divided by kilograms of solvent. So in this case, our solute, our thing that is being dissolved, is NH3. Our thing it's dissolving in, our solvent, is H2O. So in this case, molality is actually much easier to figure out because all we have to do is take how much solute, convert that to moles, and then divide it by kilograms of solvent. So right away, I already have my denominator by just a quick decimal point move. We have 0.0813 kilograms of water on the bottom for molality because we're given that information right here. To get moles of solute, all I have to do is I have to take my gram amount of solute and convert it to moles. So we take our 30.6 grams of NH3 over 1. We want moles. And then we have to divide by our molar mass of NH3, which if you look on the periodic table, it's 17.0307 grams. So we get that there are 1.80 moles of NH3 present. So right away, we can go ahead and plug that in, 1.80 moles present there. We do that simple division and we get, I believe it's 22.1 molar. So that's molality. Molarity, on the other hand, was slightly more complicated. For molarity, we need liters of solution present, and we're not given that information directly. What we are given, though, we are given how many grams of NH3 and how many grams of water. So, to figure out solution, because once again, let me remind you once again, solution equals solute plus solvent. The first thing we need to do is we need to add these grams together. 30.6 grams of NH3 plus 81.3 grams of H2O is going to give us 111.9 grams of solution. Okay, but we don't need it in grams. We need to know our solution in liters. So how are we going to figure that out? That's when the density of the solution comes into play. That's when the density comes into play for us because we know what the solution's density is, and that's going to allow us to convert between grams and milliliters. So we're going to take our 111.9 grams of solution, and we want milliliters. Okay, so for every 1 milliliter, that's 0.982 grams. So what we can do with that information, we multiply across our t-chart, we divide to solve, and that's going to give us 113.95 milliliters of solution. But we don't need it in milliliters, we need it in liters. So we have to take that decimal place and move it over 3 times. So now, over on the left, when I'm trying to solve for molarity, on the bottom, for liters of solution, I'm going to have 0.114 liters of solution. And don't forget, we already know how many moles of solute, because that's the only other thing we need. That's going to be our 1.80 moles solute. And then once we do that division, we're going to get 15.8 molar as our molarity. So once again, let me reiterate something. If you're looking at this video and going, holy crap, I have no idea how she got any of that information, I don't understand, you're probably misunderstanding something about solutions in general. Because once you understand a solution, all of this becomes easier to figure out. So again, if you're confused, please come talk to me about it. okay? Otherwise, I'm going to go ahead and move on to doing our dilutions worksheet video.